Hello, everyone. So this is going to be video lecture on section 3.3, which is basically on graphs of polynomial functions. So we're no longer going to look at just quadratic functions, but polynomial functions in general. Okay. Okay, so 3.3, oops, let me go to black. So 3.3 is on graphs of polynomial functions. Okay, so we want to talk about, actually I want to start with the short run behavior. And by short run behavior of polynomial functions, I basically mean the intercepts. So short run behavior and we're going to focus on the intercepts. Okay, so to find the vertical intercept, this is going to be exactly the same as before. So vertical intercept. Basically, I'm going to evaluate the function when the input is 0. So to find this, you want to evaluate the function when the input is 0. Or another way of saying that is if I call the input x and the output, right, the function itself y, then I want to set x equal to 0 and solve for y, right? It's what we've been doing for all of our different functions, right, to find the vertical intercept. To find the horizontal intercept, and it could be, I'll do plural because it could be more than one, then we solve when the output is equal to 0. So we set the output equal to 0. And solve for, in this case, you can think of them as the inputs, right? So if I call the, again, if I call the inputs x and the output y, then in this case, I would set y equal to 0 and I would solve for x, right? And that would give me the horizontal intercepts. So nothing new, it's just now we're going to consider general polynomials. Okay, so here's an example. Let's say I want to find the c and t intercepts of this polynomial. C of t is equal to 2t to the 4th minus 8t cubed plus 6t squared. Okay, so the c-intercept, I'll do that one first. That's like our vertical intercept, right? It's sort of like our y-intercept. Think of the c here. So I'll say the c is sort of like y, and the t is sort of like our x, right? We're just giving different names to our variables. So if I want to find the c-intercept, then I would let or set t equal to 0 and solve for c. Right? So I would make the input 0 and solve for the output value, right, which is the function value. So in this case, I would have, here's that a little bit. I'd have c evaluated at 0, right? So I'm forcing t to be 0. And if I plug in, wherever I have a t, I put in a 0 here. Well, in this case, since 0 to the 4th is 0, 0 cubed is 0, and 0 squared is 0, this is just going to be equal to 0. So the c-intercept happens to be 0, comma 0, right? Which is just the origin. So this graph passes right through the origin. Okay, now what about the t-intercepts? Well, the t-intercepts are kind of like our x-intercepts, right? So I would set the output, so I would set c equal to 0, and now solve for t. So in this case, right, I would have 2t to the 4th minus 8t cubed plus 6t squared. That's going to equal 0, right? Because I'm setting c equal to 0. And I want to solve this for t. Now, typically, it's very difficult to factor a polynomial, right, if it's larger than degree 2. So I'm either going to give you guys nice, easy polynomials to factor, or I'm going to give you them in factored form. Okay, so I will make it very straightforward. In this case, what we can do, since there's something common to every term, right? A 2t squared is common to every term. So I could pull that out front, and I'm left with t squared, right? Because 2t squared times t squared will give me 2t to the 4th. Then minus 4t, and then plus, well, 2t squared times what will give me 6t squared? I need a plus 3, right? And that equals 0. And then I could factor this piece right here. So it turns out that this is going to factor into, well, I have t times t, right? It's the only way I can get t squared. Then I want two things when multiplied will give me a positive 3, and when added will give me a negative 4. Well, if I do negative 3 and negative 1, doesn't matter which way I write them, right? So negative 3 and negative 1 will work in this case. Okay, so one possibility now is that 2t squared is equal to 0. Well, that basically just says that if I divide by 2 here, I have t squared equals 0. And if I take the square root, then I have t is equal to 0. So one possibility is t is 0. Another possibility is that t minus 3 is equal to 0. If I solve that for t, I'm going to get t is equal to 3. And then the last possibility is t minus 1 is equal to 0. And if I solve that, I'm going to get t is equal to 1. So my t-intercepts are going to be the points or the ordered pairs. First of all, 0, 0. So again, through the origin. The origin is both going to be a t-intercept and a c-intercept in this case. Then the point 3, comma 0, right? It's got to pass through that. And then also 1, comma 0. So these would be, in this case, it's going to pass through the t-axis, which we typically think of as the x-axis, at 3 different points, at 0, 0, at 3, 0, and 1, 0. Okay, here's another example. Slightly different. It's to remind you guys of long-run behavior. So that was short-run behavior. It's basically the intercepts. So this question says, find the long-run behavior of this polynomial. P of t is equal to negative 2t, t minus 1, 3 minus t squared. Okay, so what we want to do is we want to figure out what happens as t gets really, really large. So and when t gets really, really small. So as t goes to negative infinity, we want to figure out what happens to p. And then as t goes to positive infinity, we want to figure out what happens to that polynomial. Okay, so remember, that's what it means for long-run behavior. What happens as the input gets really, really large or really, really small? And the input in this case is t. Well, if you go back to an earlier section, we talked about this, and I guess this is 3.1. Remember, the long-run behavior only depends on the leading term, right, of the polynomial, the term of highest degree. So if I expand this out, so let's expand out this polynomial. So I'm going to multiply this out. I'll do 3 minus t squared first. So let me just leave this here. And I want 3 minus t squared means times itself, times 3 minus t. So if I multiply this out, I'm going to get, I guess, 9. Then I have a minus 3t, another minus 3t, so it's going to be minus 6t, and then plus t squared. And now if I distribute, or if I multiply these two polynomials, I need to multiply by the t, and then the negative 1. So here I'm going to have 9t minus 6t squared plus t cubed. Then looks like negative 1 times 9 is negative 9. Negative 1 times negative 6t is plus 6t. And then negative 1 times t squared is negative t squared. Okay, it looks like I can combine like terms a little bit inside. Let me do that. So let's see, I have t cubed, right? That's the only cubed term. And then I have a minus 6t squared, a minus t squared. So that's negative 7t squared. And then I have a 9t, 6t, so plus 15t. And then the constant is a negative 9. And then finally, I can distribute in the negative 2t. So I need to multiply that negative 2t by all 4 terms here. So negative 2t times t cubed is negative 2t to the 4th. Negative 2t times negative 7t squared is plus 14t cubed. Negative 2t times 15t is negative 30t squared. And negative 2t times negative 9 is plus 18t. Okay, so the leading term, right, the leading term, so this is p of t, is this term right here, right? This is the leading term. So when we're interested in long-run behavior, we only care about that leading term. Another way of saying it is that p of t goes approximately as negative 2t to the 4th, right? When we're talking about long-run behavior. Okay, so remember what this looks like. Forget the negative 2 for now. If I plot y equals t to the 4th, so if this were t and this were y, remember it looks like a parabola, but it's going to be flatter. So something like this, right? It'll be flatter near the origin. And then what does the negative 2 do? It stretches it, right? So the 2 is a vertical stretch by a factor of 2, and then negative flips it about the t-axis, right? So it's a vertical reflection. So in this case, this is going to look something like this. So if this is T and this is P now, it's going to be flipped and then kind of stretched like this. Okay, so now given that, we can figure out what the long run behavior is, right? So as T goes to negative infinity, so as T gets smaller and smaller and smaller, as you go in that direction, what happens to the polynomial? Well, we only need to look at that leading term, so we only need to look at that picture. It's going towards negative infinity. So P goes to negative infinity. And then as T goes to positive infinity, so now I'm looking at this side, as T gets larger and larger and larger, what's happening with the polynomial? Well, it's also going towards negative infinity. So P of T goes to negative infinity. Okay, next, I want to plot a particular polynomial function. I'll do this on Desmos and talk about like what's happening near those roots, near the horizontal intercepts. So let me load up Desmos. Give me a second here. Okay, so this is the polynomial that we want to look at. I want to observe the graph of this polynomial function. F of x is equal to x minus 1 times x minus 2 squared times x plus 1 cubed. Okay. But before we do that, let's actually figure out what the vertical intercepts are and the horizontal intercepts before we actually do the graph. And then we'll see, we'll make sure, first of all, that it makes sense, that we're getting the correct values. And we'll see what's happening to the shape of the graph. That's going to be important near those horizontal intercepts. So let's first find the vertical intercept of this polynomial function. So vertical intercept. So how do I do that? Well, I set x equal to 0 and I solve for y. I'll call this y just to make it easier. So solve for y. So in this case, right, it would be y equals 0 minus 1 times 0 minus 2 squared times 0 plus 1 cubed. Well, 0 minus 1 is just negative 1 times negative 2. It's the whole negative 2, right? 0 minus 2 is negative 2. It's the entire negative 2 being squared, so that's going to be a positive 4. And then 0 plus 1 is 1. 1 cubed is a positive 1. So this is going to equal negative 4. So it looks like our vertical intercept is going to be the point 0, negative 4. Okay, so the graph should pass through that particular point. Okay, now with the horizontal intercepts, now I set y equal to 0 and I solve for x. Okay, so in this case, right, I would set that entire polynomial equal to 0. So I'd have x minus 1 times x minus 2 squared times x plus 1 cubed equals 0. So one possibility is that x minus 1 is equal to 0, right? So let me do that here. So one possibility is the first factor, x minus 1, is equal to 0. And if I solve that, I get x is equal to 1. And since it's coming from a factor that's raised to the 1 power, you can think of this as raised to the 1 power here, then this is called some people call this like a single root or a single zero. The x coordinates of the horizontal intercepts are also called zeros, right? It's where the function where the y is equal to 0. So people will call this a single root or a single zero. And it's because of this 1 here, right? Just the 1 power. Now, if I look at the next possibility is that x minus 2 squared is equal to 0. But this really means x minus 2 times x minus 2 is equal to 0. So you could have either x minus 2 equals 0 or x minus 2 equals 0. And both of these, of course, are going to lead to the solution x equals 2. So this is x equals 2, x equals 2. But because, even though we're getting the same value, because of this squared here, we're really getting sort of 2 solutions that are the same. So this is often called a double root. Some people will say that in this case, let me go back up here. This has multiplicity 1, and in this case, it has multiplicity 2. And again, it comes from the fact of this square term there, right? Because we had x minus 2 squared. So it's x minus 2 times x minus 2 equals 0. And you're going to get a solution x equals 2, x equals 2. So it's really a double root at that point x equals 2. Okay, so in this first case, right, the horizontal intercept is going to be at 1, 0. In this case, it'll be at 2, 0, but this case is a single root, this case is a double root. And then the last possibility is I could have x plus 1 cubed. Let me do this on the next page here. So I could also have x plus 1 cubed is equal to 0. So if we expand this out, this is really x plus 1 times x plus 1 times x plus 1 is equal to 0. So we could have x plus 1 equals 0, or the same, or the same. And all of these are going to lead to the solution x equals negative 1. But so because of this 3 here, right, the cube term, this is often called like a triple root or multiplicity 3. So we call this a triple root, and we say it has multiplicity 3. But the actual location of that horizontal intercept is going to be negative 1, 0. Okay, so let's look at how this appears on the graph. Okay, so here is the graph of that polynomial function that we were just talking about. Should make this a little bigger. So you notice here that the x equals negative 1 root, which is right here, that comes from, so this is the x equals negative 1 root. Well, that comes from the x plus 1 cubed factor, right? That's how we got that particular value. So this is the x equals negative 1 root. And it comes from the x plus 1 cubed factor, right? Because when I set x plus 1 cubed equal to 0 and I solve that, I get x equals -1. Actually, I get x equals -1 3 times. That's why we say that this root has a multiplicity of 3. And if you look at the shape of the graph right near the root, it looks like a cubic function, right? So the behavior of the graph, behavior of graph near the root is a cubic function. Right? Which makes sense because it's something cubed, right? So it actually, very close to that root, it looks like x cubed, right? It looks like a cubic function. Okay, then let's look at the other two roots. First of all, this is exactly what we found, right? We found one root at x equals -1, one at x equals 1, and one at x equals 2. And we found that the vertical intercept, right, the y-intercept was at 0, -4. So that's passing through 0, -4. So it's the correct graph. So let's look at the second root right here. Okay, so in this case, this is the x equals 1 root. And it comes from the x minus 1 factor. Right, because again, if I set x minus 1 equal to 0 and I solve it, I'm going to get x equals 1. And since the exponent of the x minus 1 is a positive 1, then this is just a single root, right? It has multiplicity 1. So it's a single root multiplicity of 1. And what does the graph look like? Like, what's the behavior of the graph? Well, it looks like a line, right? It looks like just x. So the behavior is like a line, right? It looks like a linear function passing through 1, 0. And then finally, we have our third horizontal intercept, or our third root right here, right? X equals 2. So this is our x equals 2 root. In this case, it comes from the x minus 2 squared factor, right? So if we set x minus 2 squared equal to 0 and solve it, we're going to get x equals 2 and x equals 2, right? We get the same, we get like a double root. So this is a double root. You could say it has multiplicity of 2. And what is the behavior? Like, what does it look like? Well, it looks like x squared, which is a parabola, right? It's a quadratic. So the behavior is like a quadratic. So it's going to look like a parabola in this case. So it just touches the x-axis and bounces off, right? Either from a top, like in this case, or it could be from below too. It depends on the function itself. And those are really the only 3 cases that we're going to deal with. Otherwise, it gets much more complicated. Because if you had, say, an x plus, let's say it was x plus 1 to the 5th power, right? Then that factor, it would kind of look the same, but it'd be even flatter, but it's too difficult to determine. So in this case, it's either going to be a case like this, where it'll look like a cubic function, and we will assume that it is cubed, that the exponent is a 3. Or it could look like a linear function where the exponent is a 1, or it could look like a quadratic function, a parabola, where the exponent is 2. And those are the only ones that we're going to deal with in this class. The exponent will either be a 1, 2, or 3, okay, to keep things fairly simple. Otherwise, it can get really complicated. Okay. Okay, so let me explain this more carefully. So we can think of this as the graphical behavior of polynomials at horizontal intercepts, or at the roots. Like, what does the graph look like near those roots? And remember, we're only going to deal with 3 cases, with 3 different cases. So if a polynomial contains a factor of the form x minus h to the p, the behavior near the horizontal intercept which would have coordinates h, comma 0, is determined by the power on the factor, right? It's determined by the exponent. I'll write it that way. Is determined by the exponent p. Okay, and then there's 3 cases, right? So one possibility, let's say this is my Cartesian coordinate system. Let's say the function, the polynomial looks like this near the root. So in this case, we have just a single 0. So this would be a case where we have a single 0. Multiplicity of 1, or multiplicity 1. And what does it look like? It looks linear, right? If you zoom in right near that root, it looks like a line passing through. Okay, so that's the case. This would be the case if the exponent is a 1. Okay, next case. The exponent could be a 2. Let's say p is equal to 2. In that case, if you zoom, let's say the root was right here, it's a double root, then the polynomial, if you zoom in on that point, is going to look like a parabola that just touches the curve at that point there. So in this case, and it could be, I just happened to draw it opening downward, but it could also open upward, right? So in this case, we have a double 0, and the multiplicity is 2, and it looks, if you zoom in near the root, it looks like a parabola, right? It looks like a quadratic function. And then the third case is if p is equal to 3, so if the exponent is a 3, let's say the root were, right there, then if you zoom in near the root, it's going to look like a cubic function, right? So in this case, we have a triple root and the multiplicity is 3. And again, if you zoom in around that root there, it looks like a cubic function. Okay. And again, we're only going to deal with if the exponent is 1, 2, or 3. We could have higher powers as well, and then it just looks flatter and flatter and flatter. But it's going to be hard for us to determine exactly, what the multiplicity is just by looking at it, right? It depends how flat it actually is. Okay, so let's do an example here. Let's actually sketch out a graph based on some information. Okay, so let's say, actually I'm going to jump to the next page. Let's say that I want to sketch a graph of, I'll call it m of x is equal to negative 2x times x minus 1 times x plus 3. Okay, so the first thing that we probably want to figure out are the intercepts. So let's do the vertical intercept first. Well, how do I figure that out? Well, in this case, I would set x equal to 0 and then solve for y, but in this case, I'm calling it m, right? So set x equal to 0 and solve for m. So I want m evaluated at 0. So this would be negative 2 times 0. Actually, since I have a 0 out there, it looks like it's just going to be 0, right? So this will be 0 minus 1. Let's do it out. 0 plus 3. So I have negative 2 times 0 times negative 1 times positive 3. That's equal to 0. So definitely our vertical intercept is going to be the point 0, 0. So we know the graph passes through 0, 0. Okay, now horizontal intercepts. So now I set m equal to 0, right? Again, we're calling y m in this case. So set m equal to 0 and solve for x. So I would set the entire polynomial equal to 0. It's already factored, which is nice, right? So if we look at this, well, there's 3 possibilities, right? We could have negative 2x equals 0. We could have x minus 1 equals 0. Or we could have x plus 3 equals 0. And in the first case, this is going to lead to the solution x equals 0. And because the exponent here is a 1, right? That means it's multiplicity 1, so this is just a single root. In the second case, I have x is equal to 1. And again, since the exponent is a 1, it's just a single root, right? Or multiplicity 1. In the third case, I have x equals negative 3. And again, it's going to be a single root, right? So these all have multiplicity of 1. Okay, and my actual locations, the points ordered pairs of the intercepts will be 0, 0, 1, 0, and negative 3, 0. But we know that the graph is going to look like a line because they have multiplicity 1 where the graph passes through those horizontal intercepts, it's going to look like a line. Okay, the other thing that we could do is we could look at the long run behavior. So let's look at that too. That might help us with the graph. So long run behavior. All right, so first thing, let me write down the polynomial again. So it's negative 2x, x minus 1, x plus 3. Remember, the long run behavior only depends on the leading term. And last time we expanded the entire polynomial out, but really you only have to multiply the leading term for each piece of the polynomial, and that will be the leading term for the polynomial itself. So in other words, if I look at each of these factors, right, the x here is the largest term in that factor, the x is the largest here, and then outside I have negative 2x. So if I multiply those together, then I can say mx looks like, well, negative 2x times x is negative 2x cubed, right? So when we're talking about long run behavior, we only have to look at that leading term, the negative 2x cubed. Well, what does that look like? Well, remember, x cubed would be like this. This is a cubic. And then negative x cubed is going to be, so this would be y equals x cubed. But then if we want y equals negative 2x cubed, it's going to be flipped and stretched. So I guess it'll look like that. So as x goes to negative infinity, m is going to, well, as x gets smaller, 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 m is getting larger, right? It's going to positive infinity. And then as x goes to infinity, so as x gets larger and larger and larger, this is x, this is m. What's happening? Well, the function is going towards negative infinity, right? So m of x is going towards negative infinity. So when we do our graph, as x gets really, really small, the graph had better be getting larger and larger and larger. And as x gets really, really large, it had better be getting smaller and smaller and smaller. Okay, so based on all of that, let's see if we can come up with a graph. And then I'll go to Desmos and actually graph it to make sure that we were on the right track. It's hard to do this exactly, so we're just going to get a rough idea here. Okay, so here is my, let me just draw a Cartesian coordinate system. Okay, so this is x, this is really m. And we know several things. We know that the vertical intercept was at the origin, right, at 0, 0. And then we knew that we had a horizontal intercept also at 0, 0. That's one of them, right? In fact, if it's at the origin, it has to be both a vertical intercept and a horizontal intercept. We also had one at 1, 0. And we had one at negative 3, 0. Okay, so those are our 3 horizontal intercepts. Now, since all of those roots were multiplicity 1, I know it's going to look like a line going through those roots. And we also know that as x gets really, really small, the function got really, really large, right? As x went towards negative infinity, m went towards infinity. So I guess it has to look something like this, right? It has to be, as x gets small, it's got to be getting large, but then it has to look like a line going through here. At some point, and I don't know exactly where, you would need more advanced math, more calculus to figure this out, but this is going to turn somewhere. It's going to go through here, through 0. Again, it has to look linear going through 0. Then it's got to turn again, look linear. And then as x gets really, really large, it gets really, really small. Right? Remember, as x went towards negative infinity, right? So if we go in that direction, then the function was going towards positive infinity. So it was going up. So it has to look like that. And then as x was going towards positive infinity, so as x getting larger and larger and larger, then the m was going towards negative infinity. And that's what we're seeing, right? It's going down like this. Because I didn't know which way to do this, right? It could have been flipped, but this will tell me, the long run behavior will tell me what direction I need to draw this in. And then all of these need to look linear near the roots because they're all multiplicity 1. So it's going to look something like that. Okay, let me pause this. Let me go to Desmos and actually graph this and see what this looks like. Hopefully we're close. Okay, so now I'm in Desmos. I plotted our polynomial, so negative 2x times x minus 1 times x plus 3. Actually, that looks pretty good. Let me just zoom in a little bit here. Yeah, that's exactly what we were seeing, right? So as x goes towards negative infinity, the function goes towards positive infinity. So we're seeing that. There's a root here at negative 3 comma 0, and it's a multiplicity 1, so it looks linear going through. There's a root at 0, 0, and again, it looks linear. It had to turn at some point. That was difficult to figure out exactly where, but we knew it had to turn somehow, right? Because it had to go back through that root there. Then it had to turn again. And then if I zoom right in at 1, 0, again, it looks like a line going through, right? So it has to, because we know that it has multiplicity 1, same thing at 0, 0. And then as x gets really, really large, the function itself is going down towards negative infinity. So that's exactly what we expected. Okay, great. Let's do another one. I'll go back to the iPad and we'll do another one. Okay, so in this case, for my next example, I want to sketch a graph of this function. I'll call h of x is equal to x minus 1 cubed times x plus 3 squared. All right, so let's start by figuring out the intercept. So the vertical intercept, in this case, is going to be the h, right, intercept. How do I find it? I set x equal to 0, and I solve for h. So in other words, I want to evaluate h at 0. So let's see, this is going to be 0 minus 1 cubed times 0 plus 3 squared. So this is equal to, let's see, negative 1 cubed is negative 1 times negative 1 times negative 1. So that's going to be a negative 1 times, and then 3 squared is 9. So it looks like it's equal to negative 9. So the point 0, negative 9 is going to be my vertical intercept. Right? That's where it's going to cross the vertical axis, or in this case, the h-axis. Okay, horizontal intercepts. So in this case, I set h equal to 0, and I solve for x. So in other words, I'm going to set the entire polynomial equal to 0. So if I set the first factor, x minus 1 cubed equal to 0, remember, you can think of this as x minus 1 times x minus 1 times x minus 1 equals 0. Well, I'm going to get the solution, x is equal to 1, but it's a triple root, right? It has multiplicity 3. I'll just write mult of 3. So the root is going to be, or the horizontal intercept is going to be 1, 0. The root is 1. So we say the horizontal intercept is 1, 0. But it has a multiplicity of 3 because really I'm getting x equals 1 3 times, right? And the easy way to determine that is from the exponent. Remember, when the exponent is a 3, then it's a triple root. And then if I do the other case is x plus 3 squared equals 0, right? So you can think of this as x plus 3 times x plus 3 is equal to 0. If you solve that, you're going to get x is equal to negative 3, but it has multiplicity 2, right? It's a double root. Oops, let me write that cleaner. So multiplicity 2. So in this case, the root would be negative 3, 0, but it's a double root. So in this case, right, in the x equals 1 case, what is the graph going to look like near that root? It should look like a cubic function, right, near root. And in this case, where x equals negative 3, it should look like a quadratic function, right? It should look like a parabola. Okay, the other thing that we can think about is what happens with long run behavior. Because we have to know, like, as x gets really, really large or really, really small, what's happening to h? Is it getting small or getting large? So let's look a little bit at the long run behavior. Now remember, so the original function was h of x is equal to x minus 1 cubed times x plus 3 squared. So we only have to look at the leading term. But can you guys see, like, if I were to expand this term out, x minus 1 cubed, the first term has got to be x cubed plus a bunch of other things, right? And I don't even need to know those other things. I just need to know the leading term of that piece. And then if I expand this piece out, x plus 3 squared, the leading term of that piece is going to be x squared. So that means the leading term of the entire polynomial, I'm going to write it this way, it looks like x, and then x cubed times x squared, remember you add the exponents together, it would be x to the 5th. Right? You keep the base, if it's the same base, you keep the base and you add the exponents. So this function looks like x to the 5th when we're looking at long run behavior. Well, what does x to the 5th look like? Well, it's kind of like x cubed, except it just gets a little flatter, right? It gets flatter near 0, but it looks something like that. So as x goes to negative infinity, what's happening with h? It's going also towards negative infinity, right? As x gets small, h is going down. And then as x goes to positive infinity, what's happening with h? Well, as x gets larger, then the function is growing without bounds. So it's getting larger and larger. It's going towards positive infinity. Okay, so those will be helpful in figuring out like what direction to draw these things. Okay, so let me go to a new page and let's see if we can draw this function. And then again, I will plot it on Desmo to make sure that we're correct. Okay, so here's my Cartesian coordinate system. Okay, so so this is x and this is h. Now we know that, remember the vertical intercept was at 0, -9. So that's going to be this point right here. That's right here. And then the horizontal intercepts were at -3, 0. So that was here. Right, so this is 0, -9. This is -3, 0. And there was another one at 1, 0. Okay. Now, because the -3, 0, the x equals -3, that was a double root, right? It had multiplicity of 2. Then we know that near this root here, so near this point, -3, 0, it must look like a parabola, right? It must just touch the x-axis and bounce off of it. So the question is, which way do we draw that graph? Well, we also know that as x gets really, really, really small, the h is going towards -infinity, right? So we know it's coming from -infinity like this, and then it's got to hit here and look like a parabola. Okay, and why? Like, how do we know it's not coming from above? Because we said as x gets really, really small, the function went towards -infinity, so it's got to be coming from this direction. We also know that it's going through 1, 0, right? That second root, and that has a multiplicity of 3. And because it has multiplicity of 3, it's going to look like a cubic function right near that root. So it'll look like a cubic function. And we also know, because of long run behavior, that as x gets really, really, really large, the function is going towards positive infinity. Okay, so we know as x gets really, really large, it's going up, right, towards positive infinity. And then when it comes down to this root, it has to look like a cubic, so it kind of has to get flat. But then it also has to go through the y-intercept here. And at some point, I guess it's going to turn and then go back up. So it'll look like a parabola right there at -3, 0. And it'll look like a cubic function at 1, 0. It's kind of hard to determine exactly like where it's going to turn, but I think it'll do something like that. So let's actually plot this and see how close we came. Okay, so here is a graph of that function that we were just working with. So x minus 1 cubed times x plus 3 squared. And actually, it looks like we did a pretty good job. It's very difficult to get to know exactly where the turning points are and stuff, unless you know more advanced maths and calculus. But if you're getting, if you got something even close to what we got from the drawing, that will be good. And we sort of have the general idea here, right? So you can see that it's definitely going through 0, -9 as our vertical intercept. And we definitely have a point, a horizontal intercept of -3, 0, and then one at 1, 0. And let me zoom in on these. And the one at -3, 0 looks like a parabola, right? And that's what we got because it has multiplicity 2. And as x gets really, really small, the function is going towards -infinity. So that's correct. And then at 1, 0, remember, since it was a triple root, right, multiplicity 3, it looks like a cubic function. So that's what we're seeing here. Again, if you zoom in really closely, you can see it looks like, right, a cubic function. And as x gets really, really large, it's just growing without bound. It's going towards positive infinity. So that's great. So we did a decent job of graphing, at least getting the general idea of that graph. Okay, next what I want to talk about is solving polynomial inequalities. So now, instead of an equals, what if you have like greater than or less than? Like, how do we handle polynomial inequalities? Okay, so again, for this part, I want to talk about solving polynomial inequalities. Okay, so for example, let's say we're asked to solve this particular inequality. We want to solve x minus 3 times x minus 2 squared is greater than 0. So I want to figure out the x such that that is true, right? X minus 3 times x minus 2 squared is greater than 0. So the way you do this is you start by solving the equality. So change the inequality symbol into an equal sign. So I'll say start by solving the equality. Basically, that just means change the greater than to an equals, right? And solve that equation. So in this case, it would be x minus 3 times x minus 2 squared equals 0. So one possibility is that x minus 3 is equal to 0, and the other possibility is x minus 2 squared is equal to 0. In this case, right, we're going to get the solution x is equal to 3. In this case, we're going to get, it's basically a double root, right? But we're going to get the solution, because remember, this is really x minus 2 times x minus 2 equals 0. We're going to get the solution x is equal to 2, but it's a double root. Okay. Well, it turns out that a polynomial function, since it's a nice smooth function, right, it's a continuous function, it can only change from positive to negative if it even does change, right? If it passes through the x-axis, it may not. Like if it's a root 2, it could just bounce off of it. But it can only potentially change from positive to negative at those values, at 3 and at 2. So that the way that we're going to figure out when that inequality is true is by making a table. We've done this a little bit before when we did absolute value. Okay, so let me write that down here. So the function can only change from positive to negative or vice versa. It could be the other way around as well. At the roots, so at those values. So basically we can form intervals, we can form a table and test the function in each interval. Okay, so for this example, let me make a little table here. Right, so the roots were x is equal to 2 and x is equal to 3. So we want to look at, if we have two particular roots, we're going to have 3 intervals, right? So one possibility is what happens when x is less than 2? What happens when x is between 2 and 3? So when it's greater than 2 and less than 3. And then what happens when x is greater than 3? So those are our 3 intervals. So we need to pick a test point in each of those intervals. And we only need to test at one point because within the interval, it's either going to be all positive or all negative, the function, right? So what's a nice easy value to pick that's less than 2? Maybe 0 would be a nice easy value to plug in, so 0. What's something that's between 2 and 3? Maybe like 2.5. Let's say 2.5. And then greater than 3, maybe 4. Okay. So now I'm going to plug in these values into my inequality. So remember my inequality was x minus 3 times x minus 2 squared is greater than 0. So I need to plug in 0 now. So I have 0 minus 3, 0 minus 2 squared. And I want to see, I'll put a question mark here, is that greater than 0? Well, zero minus 3 is negative 3, right? 0 minus 2 is negative 2, but I'm squaring the whole thing, so that's 4. So this is like negative 3 times 4. So that's negative 12. Is negative 12 greater than 0? No, that's false, right? So that interval is not going to contain the solution. So just write false. Okay, now let me try 2.5. So if I plug in 2.5, I have 2.5 minus 3. And then 2.5 minus 2 squared, and I want to see if that's greater than 0. Okay, so 2.5 minus 3 is a negative 0.5. And then here I'm going to get 0.5 squared, right? So it's going to be positive. In fact, it'll be a positive 0.25. And then the question is that greater than 0? Well, we don't even need to actually do the numbers out. If I have a negative times a positive, that's going to be negative. Can that be greater than 0? No, so that's false. You can multiply this out, 0.5 times 0.25. So whatever that is, I guess it's negative 0.125 or something. That's a negative 0.125 is definitely not greater than 0, so that's false. But the easiest way to think about it, just look at the signs. A negative times a positive is negative, and that can't be greater than 0, so that's false. Okay, and then finally, if I plug in a 4, right, I have 4 minus 3 times 4 minus 2 squared. Is that greater than 0? So put a question mark here. So this value, it's a 1, right? But we know in general it's going to be a positive value. This is going to be a positive value squared, which is also positive. So we're going to have a positive value greater than 0. That's true, right? Whatever that value is. In this case, I mean, it's easy enough to work out. This is a 1. This is a 2 squared, so times 4. So this is going to be a 4. Is 4 greater than 0? Yes, 4 is greater than 0, so that's true. So as long as x is greater than 3, then we know that it's going to satisfy that inequality. So the solution, right, to the inequality is going to be when any x greater than 3 will be the solution. And we can write that in interval notation as parentheses 3 comma infinity, because that's typically how my open math is going to want it, right, in interval notation. So parentheses 3 comma infinity would be the solution. Okay, here's another one. Let's say I'm asked to solve x minus 1 times x plus 2 times x minus 3 is less than 0. Okay, so remember the rule is first change the less than or the inequality symbol in general to an equals sign. So this is going to be x minus 1 times x plus 2 times x minus 3 equals 0. And then solve that equation. So now it's an equality, right? It's an equation, so we can solve it. So one possibility is x minus 1 is equal to 0. Another possibility is x plus 2 is equal to 0. Another possibility is x minus 3 is equal to 0. This one's going to lead to the solution x equals 1. This will lead to the solution x equals negative 2. And this one will lead to the solution x equals 3. Okay, so I'm going to form a table now so I can form intervals and I can put a test point in each of those intervals and see whether it's true or false. Okay, so here's my table. I have 3 roots now, right? So I'm going to have 4 intervals. And you want to do, smallest to largest. So the first one is here, x equals, I guess, negative 2, then x equals 1, and then x equals 3. So the first interval would be anything over here to the left. So when x is less than a negative 2. The second interval will be between negative 2 and 1. So I'll say x is greater than negative 2 and less than 1. The third interval will be any values that are greater than 1 but less than 3. And then finally, the fourth interval is anything x greater than 3. Okay, so I need test points now. Any convenient, easy point to plug in those intervals. So I need some x value that's less than negative 2. So maybe, I don't know, maybe negative 3 is a nice, easy value to plug in. I need some value that's between negative 2 and 1, maybe 0. Right? 0 is always an easy number to plug in. Between 1 and 3, maybe 2. And then something greater than 3, maybe 4. Right? Nice, just pick a nice, easy integer that we can quickly plug in. Okay. So now I need to test these values, right? I need to test them in the original inequality. So remember, the original inequality was x minus 1 times x plus 2 times x minus 3 is less than 0. Okay, so I'm going to plug in negative 3 here. So I have negative 3 minus 1, negative 3 plus 2, negative 3 minus 3. Let's see if that's less than 0. So I'll put a question mark. And I won't even do the number. We can work out the numbers. It's pretty easy in this case, like negative 3 minus 1 is negative 4 and so on. But let's just do signs because the signs will give us enough information to tell us whether it's true or false. So this first term is going to be a negative, right? Turns out it's negative 4, but in general, we know it's going to be negative. The second term, if I have a negative 3 plus 2, that's also going to be negative, right? It's negative 1 in this case. In the third term, I have a negative 3 times a negative 3 minus 3, which is a negative 6, so that's also negative. But if I multiply a negative times a negative, it's positive times a negative, I'm going to get a negative. Is that less than 0? Yes, that's true. So this is true, right? Again, if you want the actual numbers, this would be negative 4 times negative 1 times negative 6. So if you multiply that together, you're going to get a negative 24, and that's less than 0, right? That's true. Okay, let me plug in 0, so second interval. So now I have 0 minus 1, 0 plus 2, 0 minus 3 is less than 0, question mark. Well, this is a negative. This is going to be positive. That's going to be negative. Well, what's a negative times a positive times a negative? Isn't that going to be positive, right? And that's not less than 0, so that's false. And again, if you work out the exact values, I guess it'll be a positive 6, right? So 6 is not less than 0, right? That's false. If I plug in 2, I have 2 minus 1, 2 plus 2, 2 minus 3 is less than 0. So 2 minus 1, that's going to be a positive, right? It happens to be positive 1 times a 4, but it's positive, and then 2 minus 3 is negative. So if I do a positive times a negative, that's a negative. Is that less than 0? Yeah, that's true. Okay, so that's true. And then finally, if I plug in a 4, I have 4 minus 1 times 4 plus 2 times 4 minus 3. So this is going to be a positive 3, so it's positive. This is a positive 6, so it's positive, and a positive 1, so it's positive. So if I multiply a positive times a positive times a positive, that's positive. Is that less than 0? No, that's false. Okay, so it looks like it's only true in when x is less than -2 or when x is greater than 1 and less than 3. So the solution here, so it's going to be true. The solution is going to be when x is less than -2 or x is greater than 1 and less than 3. In an interval notation, we can write this as -infinity, comma, -2, parentheses, right? Union, parentheses, 1, comma, 3, parentheses. So that would be the solution for that inequality. Okay, here's another one asked in a slightly different way. Let's say you're asked to find the domain of this polynomial function. H of x is equal to the square root of 4 minus 5x plus x squared. Okay, so remember what domain is, right? Domain are all the potential inputs that will make the output a real number, right? That you can plug in and they'll work. They won't give you any problems. You're not dividing by 0. You're not taking the square root of a negative number or anything like that. So whenever we have a case like this where we have a square root and it's an enumerator, then the argument underneath the square root, right, the radicand, has to be greater than or equal to 0. So in this case, we know that this, the 4 minus 5x plus x squared, has to be greater than or equal to 0. And actually, I'll rewrite it because it doesn't matter what order I put this in, so I'll write it in descending order because we're more used to that. So that polynomial has to be greater than or equal to 0. So really this becomes an inequality problem, right? We're solving this polynomial inequality. Okay, so remember the first step is to set it equal to 0. So change that inequality to an equals. And solve this. Well, okay, it's not in factored form, but it looks like this is not too bad. It looks like we can factor this. So let's try this. So the only way I can get x squared is x times x, right? Then you want to think of, well, I need two things when multiplied will give me a positive 4, and when added will give me a -5. So two things when multiplied will give me a positive 4, and added will give me a -5. Well, -1 and -4 are going to work, right? It doesn't matter what order I write them in. I'll just do -4, -1. Okay, so one possible solution is x minus 4 equals 0, and the other one is x minus 1 is equal to 0. So this one's going to lead to the solution x equals 4, and this will lead to x equals 1. So now if I make my table, so this is x equals 1. Remember, you want to do lowest to highest, right? And x equals 4. So this interval to the left here is anything x less than 1. This is between, so greater than 1 and less than 4. And this would be anything x greater than 4. So let's pick some test points. Less than 1, well, easy one is 0, right? Between 1 and 4, maybe 2 or 3. Let's do 2, let's say. And then greater than 4, let's test 5. Okay, so I need to test this now. And actually, it's easier to plug it in when it's in factored form, right? So remember, the original inequality is this right here. But we factored this, right, to be x minus 4 times x minus 1 is greater than or equal to 0. And it's easier just to plug into things when they're in factored form. So I really want to use this form right here. Okay, so I have x minus 4 times x minus 1 is greater than or equal to 0. All right, so if I plug in 0, I have 0 minus 4, 0 minus 1, greater than or equal to 0, right? Question mark, because I'm testing it. Well, this is just negative 4 times negative 1, so that's positive 4. Is that greater than or equal to 0? Yep, that's true. So the solution is definitely in that interval. Now let me check 2. So I have 2 minus 4 times 2 minus 1, greater than or equal to 0. Let's see, so this is going to be a negative 2 times 2. Again, you can just look at signs, right? You know this is going to be negative times a positive. That's negative. And that can't be greater than or equal to 0, so that's definitely false. And if I plug in 5, I have 5 minus 4 times 5 minus 1. So this is 1 times 4, or you can just think of it as a positive times a positive. So I'm going to get a positive, in this case, a positive 4. That's definitely greater than or equal to 0. So this is true. Okay, so my solutions are going to be when x is less than 1, but because I also have the equal sign, right? The original inequality was greater than or equal to. It could also equal 1 and it would still be true, right? So x is less than or equal to 1 is one possibility, or x is greater than or equal to 4. So in interval notation, the domain is going to be from negative infinity to 1. In this case, including 1, right, because I have the equals. And then union 4, including the 4, so I'll do a square bracket, 4, comma, infinity. Right, and that will be the particular domain. Okay, so the next thing I want to talk about is, given a graph of a polynomial, sometimes we can write out the function, right? As long as it's not too complicated. So I want to show you a few examples of that where we can write out the function given the graph. Okay, so there's one last thing I want to do for section 3.3. So you can sometimes write the function, the polynomial function itself, given the graph, as long as it's not too complicated. So let me explain how you can do that. So you can sometimes write the function of the graph. So the polynomial in general can be written in the following way, right? You can write it as f of x equals, there's going to be some constant out front, I'll call it a, that we'll have to figure out later. And then it's going to be x minus x1, where x1 is like your first root, to some power, we'll call it p1, and then x minus x2 to p2, dot, 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 right? You can keep, it depends how many factors you have, all the way to, I'll write it as x minus xn to the pn. So the powers, those can be determined by the behavior of the graph, right? So where the powers, I'll call it p sub I in general, right? So p1, p2, all the way up to pn, can be determined by the behavior of the graph. And really what we mean by that is by the behavior of the graph near those roots, right? Near the x-intercepts. So behavior of the graph, I'll say near the roots. So if it looks linear, then we know that the p is going to be, the power is going to be a 1, right? The exponent will be a 1. If it looks like a parabola, quadratic, then we know that the power or the exponent is going to be a 2. And if it looks like a cubic function, then we know the power is going to be a 3. And then the a, so that value up front, can be determined just by plugging in a point, right? We've done this before. So it can be determined by plugging in a point on the graph. The only thing is you can't use one of the roots because it'll make it 0 and it won't allow you to find a. So I'll just say use a point other than the horizontal intercepts. Okay, and that will allow us to find a. Okay, so let's do an example. I guess I'll go to Desmos to do this so we can actually see the graph, and then we'll see if we can come up with the actual equation, the actual function itself. Okay, so here is the graph of our polynomial. And given this graph, we want to see if we can determine the equation, determine the actual function of that polynomial. All right, so the first thing you want to look at are the roots. So if you look in this case, let me annotate this. It looks like we have a root at -1. Right, so we have the root x equals -1. And by looking at the shape right near that root, what is the multiplicity? Well, it looks like it's multiplicity 2, right? It's a double root because it looks like a parabola near that root. So we know it has multiplicity 2. That means the factor that gave rise to that root is going to be x minus a -1, and then it'll be squared, right? Because it has multiplicity 2. Squared. And of course, we can write that as x plus 1 squared. Okay, and then the other root here is this root right here at x equals 2. So we have a root of x equals 2. If you look at that, it looks like a line passing through, right? So it just has multiplicity 1, or it's a single root. That means the factor that it came from was x minus 2 to the 1 power, so that's just x minus 2. So that's the particular factor, okay? So that means the polynomial itself, I guess I can do this all on here. I'll write it up here. The polynomial itself is going to have the form f of x is equal to some value, I don't know what that is yet, a, times x plus 1 squared, right, times x minus 2. And we just need to figure out what that a is, right? And then we'll have the exact equation for our graph. Okay, so how do I figure out the a? Well, I can just plug in any point that I want to plug in, but you can't use one of these horizontal intercepts, right? You can't use the roots, because if you plug in a root here, like if I plug in -1, that means it's going to make the whole thing 0, and it's just going to say 0 equals 0, which is true, but it's not going to help us find a. So you want to use some other point that lies on the graph of this polynomial that we can plug in. And typically what you would do, as long as it's not at the origin, is to use the y-intercept, right? Use 0, 2, because that's a nice easy point to plug in, and that'll help us find a. So if I plug in 0, 2, let me go back to the iPad to finish this. Okay, so right now I have that graph is going to have an equation, right? A function that looks like this. F of x is equal to a times x plus 1 squared times x minus 2. And we're almost done. We almost have the actual function that we want of that polynomial. The only thing we need to figure out is the a. So to do that, we're going to plug in a point, but it can't be one of the roots, right? One of the horizontal intercepts. So we're going to use the vertical intercept, which was the point 0, 2. So we're going to plug in the vertical intercept 0, 2 to find a. Okay, so where I have a y, or my f of x, which is really my output, my y, I plug in a 2. And where I have an x, I'm going to plug in a 0. So I have 2 is equal to a times, well, 0 plus 1 is 1, 1 squared is 1, so this is a 1 there. And then 0 minus 2 is a -2. So this is telling me that 2 is equal to 1 times -2 is -2a. And then if I divide both sides by -2, I'm going to get a is equal to -1. So that means my polynomial of that graph is going to be f of x is equal to negative, or you can write -1, doesn't matter. You don't really need to write the 1, times x plus 1 squared times x minus 2. So that would be the actual equation of that graph. Okay, so that's the function of that particular graph. All right, let's do one more example. So I'll go back to Desmos and give you another graph, and we'll reason it out and we'll try and find the equation of that graph. Okay, so here's the graph of the polynomial that we want to try and figure out the function of, right? The equation for this particular graph. So if we look at this, in this case, let me zoom in a little bit more. In this case, it looks like I have a root at x equals -1. Okay, so there's a root at x equals -1. And if we look at the behavior of the graph near that root, it looks like a parabola, right? Like a quadratic. So in this case, it has multiplicity 2. That means the factor that the root came from must have been x minus -1. And then it had to be squared, right? The exponent must have been a 2 because of the multiplicity 2. And of course, x minus -1 is the same as x plus 1. So the factor is really x plus 1 squared, right? That handles that root. Then let's see, we have another root here at x equals 2. So there's a root x equals +2. And if you look at that, if you zoom in closely, it looks like a cubic function, right? So this has multiplicity 3. So that means the factor that that root came from was x minus 2 cubed. Okay. And then finally, I have one more root right here at x equals 4. So I have a root x equals +4. That looks like just a line passing through, right? So the multiplicity is 1, or it's a single root. That means the factor that gave rise to that root was just x minus 4, right? Raised to the 1 power. So I can just leave it as x minus 4. So if I multiply all those factors together, right, I'm almost done. I know that my polynomial is going to have an additional a in it. Let me do that over here. So my polynomial, oops. So my polynomial, right, will look like f of x equals, there'll be some factor a, then I'm going to have an x plus 1 squared times an x minus 2 cubed and times an x minus 4. Right, and that'll give me, that'll be the equation of that particular polynomial. So what I need to do is I need to figure out what that a is. Okay. So again, let me go back to the iPad using Biddle, and we'll finish up this problem. Okay, so for that particular graph, right, that polynomial, we figured out most of it so far, right? So we have f of x is equal to a times x plus 1 squared times x minus 2 cubed times x minus 4. And we need to figure out a, so we need to plug in a point that lies on that graph, right, to figure out a. And if you noticed, the easiest point to use was, again, the vertical intercept, right, the y-intercept. So and we can't use the roots, right? We can't use the horizontal intercepts because they're not going to help us, right? If we plug in -1 or +2 or +4, I'm just going to get 0 = 0. That's not going to help me find A. So I need to use something else. So typically we're going to use that vertical intercept. So in this case, the vertical intercept was 0, -4. So I want to use the point 0, -4 to determine A. Okay, so when the y, the output, is -4, the x is going to be 0. So I need to plug in 0 here. Okay, so I have -4 is equal to A. Well, 0 plus 1 is 1. 1 squared is just 1. 0 minus 2 is -2, but -2 cubed is a -8. And then 0 minus 4 is a -4. So I have 1 times -8 times -4. It looks like that's a positive 32. So this is saying that I have -4 is equal to 32A. And then finally, I can solve for A by dividing by 32. So it looks like A in this case, if I simplify that, it's going to be -1/8, right? Because 4 goes into 32 8 times. Great, so we found A. So now the final answer, right, for our function will be f of x is equal to -1/8, that's our A, times x plus 1 squared times x minus 2 cubed times x minus 4. And that's correct, because this is the equation I plugged in to generate that graph, right? So we came up with the equation, the function, given the graph. And again, I'm only going to give you cases where the exponents here, right, the powers, are either going to be 1, 2, or 3. We're not going to do anything more complicated than that, because it really is almost impossible to determine exactly whether it's 5 or 7, depending on how flat it is. So it'll be the most complicated case will be a cubic, right? It'll be a 1, 2, or a 3. Okay, excellent. So that's it for 3.3. And then the next lecture, we're going to jump to 3.7, which is on rational functions. That'll be the last section that we do in chapter 3. And then we can start looking at chapter 4. And chapter 4 is going to be on exponential functions and log functions. So exponentials and logs. All right, great. Thanks, everyone.